Bismillahirrahmanirrahim. So today we will study binomial random variables. If you can understand binomials, then everything else is just a simple extension. Now, I have a full lecture on the derivation of the binomial probabilities, so I will refer you to that to understand where the formula comes from. But so I will explain just the meaning and use of the formula here. So first we consider the concept of a random draw. So here we have a population. We've already discussed that population can be anything, but now we consider a population of just two elements. One of the element is the number 0 and the other element is the number 1. So there is a population which has two things in it, and so what we do is we draw at random from this population, and the probability of drawing 1 is equal to P, and the probability of drawing 0 is equal to 1 minus P. This is the basic binomial random variable. Actually, the model that I am following, all of the tickets should have equal probability. So this is not actually in conformity with that model. But it's very easy to fix. Suppose that P is 70%. Then what we do is we create a box in which there are 70 ones and 30 zeros. Then all of the tickets have equal probability, and we pick one at random, so the probability of 1 will be 70%. So I just use this as a shortcut. It is not a serious extension of the basic model. The basic model is that in a box we have tickets. All of the tickets have equal probability, and P of them have 1 written on it, and 1 minus P% of them have 0 written on it. So as a shorthand, I say, okay, we pick one with probability P, instead of writing out the details. Now, this 1 is called a success and 0 is called a failure. This is just to help us keep track of things. So then we can make multiple draws from this same box, and again the conditions of drawing are IID, independent and identically distributed. So D1 is my first draw. I draw at random, and it's either a 1 or a 0. The second draw, it's again either a 1 or a 0. Third draw. So at the end I get a sequence of zeros and ones. 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, something like that. So now I can take the sum of all of these zeros and ones, and that is the sum, which is D1 plus D2 plus up to Dn. And basically S is the number of successes. It just counts the number of successes. So this number of successes, S, is a binomial random variable with the N being the total number of trials and P being the success probability. And now the most fundamental and important theorem is that the probability S equals K is given by N choose K, which is N factorial over K factorial times N minus K factorial, times P raised to the kth power times 1 minus P to the N minus K power. So this is crucial, central. This is something that you should really work on understanding in detail. This is the brick upon which everything else is built. And I have a whole lecture 13 of Introstats, which has a video also and exercises and everything to explain this formula in great detail, where it comes from. Now, what we are going to do is build upon this and consider many properties of the binomial. Basically, everything that is in statistics and in probability can come from the properties of the binomials. So we start with the simplest properties. First of all, the largest binomial probability occurs at integers closest to NP. What is this saying? This is saying that how many successes do we expect to see? So the probability of success is P, the total number of trials is N, so we should see about P times N successes. And so the probability of an integers, Pn may not be an integer, but integers near to NP will have high probabilities. This is the basic one result. In fact, what you can show is that the integer closest to NP, either the one less than that or the one bigger than that, generally has the highest probability. Then all the probabilities decrease on each side. So you have a maximum and then probabilities decrease away from that. So it's a very nice unimodal distribution. There is no funny business that it goes down and then it goes up again and so on. So n is the most likely, Pn is the most likely number of successes, and then as you move away from this number, the probabilities decline. They decline to 0 as you move away from the center. And the third probability is actually an asymptotic thing, which we will discuss later, that all probabilities go to 0 as n increases. So this is actually a bit strange and against the general intuition that people have. People think that the NP probability will go to 1, which is actually something which is very close to what the law of large numbers says, that the true probability will match the sample success probability in large samples. This is actually true, but it doesn't mean that the probability of the exact match is going to 1. Probability of exact match goes to 0.
P is the probability of success and 1 minus P is the probability of failure.
Yes.
Then slide number 3, sir, kindly. Slide number 3. Sir, when you were writing the formula NCK, P raised to power K?
Yes.
Not P raised to power N.
No. Alright, so here is an illustration. Suppose X is binomial with 23 trials and 70% success probability. So we have 23 trials. In each trial, the probability of success is 70%. And so what is NP? 70% of 23 is 16.1, which is not an integer, but 16 is close to that. So we expect that the probability of X equals 16 should be the highest, and then it will decline away from it. And that is what the picture shows. The picture and also the table. In the table, the probability of 16 is 17.82%. And the probability of 17 is 17.12%. So these are the two numbers which are the closest to NP, 16.1. So 16 is higher and 17 is a little bit lower. Then you see that the probability started declining. So if probability of 15 is 15.2% and 18 is 13%, and so the table shows how the probabilities start to go to 0 as you move away from the true success probability, which is 16.
Sir, is it NP, is it mean of this distribution, NP?
Yes, mean of the distribution is NP. So the mean is 16.1, but 16.1 is not available to the binomial. Only 16 is available and 17, because the binomial can only have integer values. So you can either have 16 successes or 17 successes. You cannot have 16.1 successes. So now the next thing. Next thing I want to show is that the probabilities decline to 0. So this is part of asymptotics. That's really where the whole game is. What happens for large n? This is what asymptotics means. What happens for large n? So what we see here is that the peaks are higher. Here the graph is for going from 60 to 80. It is the central values, because so 70 is the this is for n equals 100. So this time we have 70 is exactly the 70%, and it has the highest probability, which is about 0.088% is the probability of getting exactly 70%. And if you look at the range from 60 to 80, you have most of the probability, but probability still exists in the other parts. I just calculated these probabilities here, and I wanted to show you that. Okay, so this is the binomial distribution with 170% probabilities, and it starts here. Notice what I have written. This is actually the 2013 version. The name keeps changing. In the older versions, you have binom dist, and here you have binom dot dist. And then I have given the k as row blank blank, so paren. So that means that the k is equal to the row number, which is 3 here. So what is the probability of 3, x equals 3, given that the total number of trials is 100 and the probability of success is 70%, 0.7. I'm reading the status bar fx here. And then you have false. What is the false doing here? Yes, exactly. By default, this is cumulative distribution, and so if I put true, it will give the probabilities up to 3. So it will be probability of x equals 1 plus 2 plus 3. Sorry, probability x equals 1 plus probability x equals 2 plus probability x equals 3. So I have made that false, so it's giving the probability of just exactly x equals 3. And it's a very, very small probability, e to the minus 46. That means that there are 46 zeros before the 1. So this event, so you have to learn to understand these numbers. Suppose that we have we are doing this trial in which there is a success probability of 70%, and we count the number of successes. So what is the chance of seeing 3 successes? Very, 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 very small. Suppose I do a trial every day, then 1,000 trials will take 3 years. That's 3 zeros. So 3 zeros is 1,000 trials. Million. So if we take 1,000,000 years, that's 9 zeros. Billion years, that's 18 zeros. We still are very far away. So in 1 billion years, if I do this trial every day, I will never see 3 successes because it's too low. With 70% success, you will see many more ones, and the chances of seeing 3 zeros are almost none. Now we keep going up, you see. So These numbers are very, very small. Now we start to get numbers which are seeable. Let's look at this, the first number which is not in scientific notation. So 53, this has a chance of 1 followed by 3 zeros. So if we convert that to 1,000, 10,000, yes. So if we have 10,000 trials, then you will see one case in which you have 53 53 successes. So I'm flipping a coin, or I'm doing something. Let me put it that, okay, so you have a university where 70%, like NUML, 70% of the students are females and 30% of the students are males. And so every day you pick a student at random and you give them a prize, or actually, it's not like that. You give, you pick 100 students at random and you give them all prizes. No, not like that. You pick a student at random, and if it's female, you record a success. Okay, that's not a very good one. Okay. Every day in the hospital, you get 100 patients of dengue fever. That's very large contagious population, and you have a treatment which cures 70% of them. So every day, the probability of curing a patient is 70%. All right, so this is now a reasonable model. Okay, so every day the hospital gets 100 patients. That's the capacity, and the disease is running rampant. So every day the hospital is at full capacity. Now every day 100 patients come in, and you give them the treatment, and either they recover or they die. 70%. The chances of recovery for every patient is 70%. So every day, some patients will recover, some will die, and the number will vary because it's independent. It's not going to be 70%. Even though the probability is 70% for each patient, the number of patients that you see on any given day will be different from 70. In fact, the probability of 70 is 8%, right? We have already calculated that in the previous table. So we can ask, on how many days will you see, suppose process is going on. Every day 100 patients come in, you give them the treatment, and those who recover walk out, and those who don't go to the graveyard. So now every day we ask how many patients walk out the door. So on some days you have 50, some days you have, actually you never have 50 as you see. But some days you have 60, some days you have 80. Now you ask the question, on how many days will you see 70 patients go back home? The 70% is the true probability. So this is one of the key things that students keep making mistakes about, that there is the true probability and then there is the observed proportion, and the students keep confusing them no matter how much you teach. I had a PhD student who made a mistake and confused the observed probability and the true probability, making all his calculations wrong. A paper was published based on these wrong calculations. I had to withdraw that paper and say that this is completely wrong, and all the calculations were wrong because he did not make the difference between the true probability and the observed probability. So the true probability is 70% every day. It doesn't change. The observed number of patients who recover changes every day. Sometimes it's 71, sometimes 75. On one day it's 65, and so on. So we ask the question, suppose that the hospital goes on for, this process goes on for one whole year. On how many days, let's say 300 days to make life simple, how many days will 70 patients walk out the door? Not 8, but 8 is a good number to think about. 8% is the probability. 300 days. 24, exactly. What's your name? Oh, I owe you a chocolate. I didn't bring it. All right. Rabia has a chocolate. Now, this probability is 0.001. How many years will we need in order to see a day in which 53 patients walk out the door? In 10 years, we will have 3,650 days. So, yes, somebody else wants a chocolate? Come on, it's not that difficult. What's the probability here? Yes. So this is 1 in how many?
10,000.
1 in 10,000. So how many years will it take before this event happens? Yes, 3 years. Sorry, not 3 years. Wrong. 30 years. 3,650 is the number of days in 10 years. So 30 years it will take to get us to 10,000 roughly. And so in 10,000 days we will see this event once. So this is to understand. You see, you have to understand probabilities intuitively. So you understand that this is the why is this probability so low? This is also important because 53 is too small a number. With 70% probability in 100 trials, 53 is too low. You don't expect to see that too often. So this is telling us, you see, how, you see, on the one hand, you see, person who doesn't know about probability theory, and this is going to be the difference if you learn, the person who doesn't know about probability theory, when you look at this table, the table says that all numbers from 0 to 100 have non-zero probability. Everything can happen. Probability x equals 0 is 1 e to the minus 46, so it can happen. Probability that x equals 100, it also has a small probability, but it can happen. So anything can happen. Now this is true, anything can happen, but the probability that x equals 53 can happen, but it will take us 30 years before we see one such event. Who came up with the 31st? There were lots of mistakes. So, all right. So we keep going. 53 के बाद क्या हो गया यहाँ पे? Slow हो गया यहाँ पे. Oh yeah. Oh, I'm looking at the wrong column. Okay.
57.
Okay. So 53 is now the probabilities start increasing. So 56. Easy chocolate. How many years will it take for us to see a day in which there are 56 patients who walk out the door? 3 years, exactly. बहुत हल्के से बोला था किसने? अच्छा, मारिया कुत्ती जाने था. No chocolate for you. Alright, so I start making the table at 60 because the numbers are now getting reasonable. So at 60 it's 008. At 61 it's so 008 means that in 1,000 days, in 3 years, you will have 8 days in which you see 60 patients walk out the door. This is still too low. Now we get a big number compared to these small numbers. 61 patients. Now there will be 12 days or 13 days, 129, 13 days approximately in 3 years that you will see 61 patients, meaning that this is still a very small probability event. So you see, one thing with very important philosophical issue, people like to be certain. I would like to say something that this is true 100%. The price of certainty is that you can't say anything. Because if you say that I want to say something about what will happen with 100, that is true with 100% probability, the only thing you can say is that it will be some number between 0 and 100, which is not useful. So now if I want to say something with 99.9% probability, so it will be true it will be true 999 times, and it will be false one time out of 1,000. So then I can say that 1 in 1,000 is at 57, that the number will be between 58. The number of successes will be between 58 and 78 12 देना, तो other side पे भी वही लेना होगा, तो 82 roughly. This is not actually a correct calculation because I have to sum over a lot of numbers, but we will show how to do the correct calculation. But roughly speaking, from 58 to 82, this is the range in which if I say, okay, I'm going to predict that the number of patients will be between 58 and 82 who will walk out this door today. So my prediction is not 100% true. I might be wrong. But 99% I am sure. So in 100 days, 99 days I will be correct. And one day I might not be correct. So this we call confidence. This is different from probability. And you have to, and this is again a big source of confusion. That confidence statements are, I am making a sentence and it may be false. A probability statement is always true. If I say that the probability of your recovery is 70%, this is always true. But what will actually happen is that either he will recover or he will die. So only one of these two. There is no 70%. 70% can never be observed. This is the thing. Probability statements are about unobservables, and confidence statements are actually different. They are about things which are true or false. So I can say that I am hopeful you will recover. So this is a statement in which I can have 70% confidence. It is not the probability statements. Probability statement, confidence statement is about something which will happen or which will not happen. So that is not a probability statement is different. It is invisible. The probability is always invisible. It can never. It shows itself in this exactly pattern that the different numbers will come out with different probabilities. So the 70% has 8.6% probability. So in 1,000 days, how many days will we see 70? Yes. In 1,000 days, 86 exactly. So you see, this is again something which the students have difficulty with. I am trying to explain those issues where students are often making mistakes. So one of the strong and common misconceptions that students have is that this number will have high probability, 70, and it will keep increasing, because that's what the law of large numbers says. Law of large numbers says approximately that the probability of seeing 70%, the observed frequency converges to the true probability. This is true as n goes to infinity. So the observed frequency will actually converge to 70%. So they think that, and the probability of this event goes to 1. So they think that the probability of 70 is going to 1. But this is not true. Actually, the probability of 70 is going to 0. Probability of 70% is going to 0. This is exactly the opposite of what you tend to believe. So, okay, so we have this. Now, the second table is for 140. I haven't. If you look at the status bar, so it says binom dist of row 200, 0.7 and false. So now we are moving from, this is the asymptotics, we are increasing the n. So now the probabilities will be from 60 to 80 will now be at 120 to 160. So there is nothing here near 60 to 80. These are too small numbers, because in 200 these are too small. Now we go down, and here it is 120. This is the counterpart of 60. We have changed sample size n from 100 to 200. So the 60 has moved to 120, and this has a probability 0.006. It keeps going, and the probabilities keep increasing. 140 is the most likely number. 140 out of 200 is 70%, but the probability of 140 is 6% instead of 8%. So you see, the probability of exact match to the true probability is going down and will go down to 0. क्या हुआ?
Sample size पे बढ़ाने से.
As the sample size increases, the probability of exact match to the true probability goes to 0. This is exactly the opposite of what the law of large numbers says, which says the law of large numbers says that the probability of an approximate match to the true probability goes to 1. So there are two opposite things which are happening. The exact match is going to 0, approximate match is going to 1. And we will see both of these things. Alright, so what's happening here? The graph is over here. And basically, in this case, in the previous graph, 100, there was some probability, some serious probability outside of these bounds, outside of the 60 to 80. But now there is no serious probability outside of these bounds. You see, what has happened is that 60 to 80 converted into 120 to 160. So 20 points converted into 40 points. The probability went down, but not by half. This is very important. And it is also important to know why it didn't go down by half, how much it went down by. All of these things we will discuss later. And all of these things you have to know as a student of probability. And these are very simple formulas that you can use to calculate. And if you know these things, then you can learn a huge amount of material. Now, I have found a very shortcut through the path which took me things which I learned in years and years. I am trying to teach in days and days, which is because I've eliminated all of the unnecessary material. But there's still some learning required. You have to invest in days and days in order to learn. You don't have to invest years and years. So the peak has gone down, but not by half. Actually, the peak goes down by the factor of the square root of n. So you are multiplying the probability by 1 over square root of n. So if you double the something, then the number that the decline takes place by 1 over the square root of 2, or 1 over 1.4. So this is not instead of 1 over 2, which is what we would expect. So 1 over square root of 2. So it's not half. So you have doubled the number of points, but you have decreased the probability by only a factor of about 2/3. Then it means that the total probability in here has increased, right? Because you have doubled the points, but not half the probability, more than half. So basically that's what's happening. Within the same range of probability, if you take the same interval and you upscale it, keep increasing n, the probability in that interval will go to 1. Because all of the probability will enter into this eventually. So this is what. So if you take a fixed percentage interval, then in that fixed percentage the probability will go to 1. But the number of points coming into that interval will increase to infinity. The probability at each point will go to 0. But the total probability, when you sum over all the points, that will go to 1. Okay, so the peaks are higher, the total probability is lower. And the second graph, the peaks is lower, but there's 2 times the number of points, but the peaks are not half as low, so the probability is more. And we can actually calculate that, how much, and so on. And we will do that actually soon. All right, so one set of properties. Now the second set of properties is obtained by is all asymptotic properties, and the key thing is de Moivre's theorem, French mathematician. So he says that all of these things are related to each other. That if you want to look at the 95% interval, this 95% interval is going to be very important, because basically, as I've told you, we cannot make 100% true statements. So we have to relax our standard. So one standard is 95% confidence. So we say, okay, what is it that I can say with 95% confidence? So that's just a convention. And 95% we can say is fairly often. Actually, I have words for this, and that's what we need to know. I mean, probability teaches us how to make statements which we are nearly certain. That's what I use for 99%. We can be fairly confident. Highly confident is 95%, and then 90% is also possible. Okay, so if I want to get 95%, then NP by itself, as I said, the probability of NP is going to 0. I have to extend the interval in order to catch more probability. So how much do I need to extend it to catch 95% probability? And again, this is asymptotic. So this is true for large n. How large the n has to be, that's again a question that we will consider. But basically NP plus or minus 2 times the square root of NP1 minus P is a 95% interval. So if I take NP and I extend this to this range, then I will catch about 95% of the probability. And if I say that, okay, the number will be between, I make this calculation, I say, okay, it's going to be between 65 and 75, then I can be 95% certain. What does 95% certain mean? It means that in 20 days, I will be wrong 1 times, and I will be right 19 of those days. Alright, now if I define M equals NP, M is the mean, and if I define S equals the square root of N times P times 1 minus P, then that's the standard deviation for the binomial. And now I define Z equals X minus M divided by S. So this is actually called a standardization. It's very important to understand the concept of standardization. Any variable can be standardized by subtracting the mean and dividing by the standard deviation. So I standardize my binomial variable by subtracting the mean and dividing by the standard deviation. Then basically this z becomes normal for large n, and that is the content of de Moivre's theorem. De Moivre's theorem says, one way to state it, there are other ways to state it as well, that if you standardize a binomial random variable, it becomes normal for large n, standard normal for large n. So the probability can be written in terms of a normal integral, and now I will carry out this process to show what this means. This is the most important and fundamental thing to understand. Once you understand this, then everything else follows from this. So this is a very important brick. Okay, so I'm going to illustrate this. You see, I'm just trying to tell you a learning tactic. This is something which is very important to understand. In the mathematics, we have theorems, and then we have concrete illustrations. For example, there is the commutative law of algebra, which says that x plus y is equal to y plus x. Now, if you want to understand this, then what you see in the mathematics text, you will see a proof of something or the other, or you will see that as this is an axiom. But to understand this, you have to always translate it into concrete terms. What does it mean? So you can say that 8 plus 6 is equal to 6 plus 8. So this is an illustration. So there is a generalization and then there is a particular. You have to think simultaneously on both ends. And if you don't understand the generalization, translate it into a special case, try to understand it, then go back, and maybe you still will not understand, then do another special case. So the understanding always goes from the particular to the general. But the textbooks are written in the opposite way. The textbooks start with the general and go to the particular, and this is very harmful for learning, because students read the theorem and they say, oh, I can't understand it, and then they come to the particular and they just go through the motions of, but they have already been defeated, because they have said, oh, this theorem is beyond my understanding. So if you do it the opposite way, start looking at illustrations. For example, very simple, in grade school you learn about how to add fractions. So if you have 3 plus 5 plus 4 plus over 7, 3 over 5 plus 4 over 7, you say, okay, this is the rule. You multiply the denominators together, and then you multiply the cross multiply and add. Okay, you can learn the rule. What does it mean? Why does it work? That's difficult. But if you work hard on it and you understand a lot of particulars, then eventually you will be able to understand the general. So here I have given a theorem, hard to understand. Now I'm going to illustrate what it means in a particular case. And if you understand how to use it in special cases, then eventually you will come to understand the general. So x is binomial n 70%, same example as before. So what is m? The mean is 70% of n, whatever n may be. And what is the SD? S is equal to square root of np, 1 minus p. Now I can calculate p is 70%, 1 minus p is 30%. Multiplying the two, we get 21%, 0.21 is 0.7 times 0.3. And then if I take the square root of 21, then I get 0.458. Let me just show you so that nothing is hidden. Where is the calculator? No calculator? Acha.
top one.
कहाँ पे?
Start menu.
Oh, right. Okay, so 0.21 and then where is the square root?
व्यू पे जाएंगे सर.
है? View पे? अच्छा.
इधर से साइंटिफिक करने इसको.
Okay.
0.21 again.
Oh, अच्छा. स्क्वायर रूट आता है यार इस पे, उसमें पहले भी आता है यानी विदाउट द साइंटिफिक, मगर आई डिडंट फाइंड इट. चश्मा भी नहीं है. Okay, here's the square root. So it's 0.45825575 वगैरह. खैर, so to 3 decimal places it's 0.458. So the standard deviation is 0.458 times the square root of n. And now what we can say is that for large n, z equals x minus m over s is approximately standard normal. Now to illustrate how we use this, suppose I want to calculate the probability that x is between 65 and 75. Okay, so now I'm going to show how this normal approximation is used. You've all done this, but this is very crucial, basis of everything. So what we do is first we make a continuity correction because 65 is an integer exactly. So the calculation for 65.1 will give a very different number, and for 64.9 it will give a very different number because the integer introduces a discontinuity. So the thing to do is to calculate at the midpoints. That gives the better results because the midpoints are farthest away from the integers. So we look, instead of looking at 65, 75, we look at the probability for 65.5 to going to 74.5. So now there is no need for knowing whether this is strictly less than or equal to. Both of them will give exactly the same result. Whereas this does not happen at 65 and 75. We change the less than to less than equal, again you get different result. So now what is m? M is 70% of 100, that's 70. What is s? Square root of n, since n is 100, that's just 10. So s will be 4.58. Now we convert the variable to z. So we have x minus 70 over 4.58. And we have to convert the limits also. So we do the same thing to 65.5 and 74.5. So if 65.5 minus 70 over 4.58 is less than x minus 70 over 4.58 is less than 75.5 minus 70 over 4.58. So now we can calculate, these are just three numbers, and it comes out to minus 0.982. I can do it on the calculator, but I think you can do this much yourself. Less than z is less than plus 0.982. And now I can calculate this according to the normal distribution by using the normal distribution. So if I look at Excel, I have this calculation. So norm.s.dist. Now in the previous version I think it's norm s.dist. Plus 0.982, and true gives the probability that z, the normal variable, standard normal, is less than 0.982. To get the probability in this range, I have to subtract from this the probability that z is less than minus 0.982. Right? These are calculations that should be familiar. So, of course, these two things add to 1. So once I have 0.837, I can calculate the other probability as the difference between that and 1, and that's 0.163. And if I subtract 837 from 0.163, I get 674, which is the desired probability. Now we will check it in Excel. So you need to get confidence in these formulas by seeing that they work. So here it is. This is the normal approximation. norm as dist plus 982, norm as dist minus 982, and now let me just do a subtraction, equals this minus this. Check. So that's 0.67390. That's the normal approximation. Now, what is this 674? That's just, I'm taking the sum from 66. Remember, this is 65.5. 66 up to 74. B66 to B74, that's 674. And notice how 6740, this is almost the same as the normal approximation except for a difference in the fourth decimal place. So this shows that our central limit theorem is working as we increase the normal probabilities and as we increase n, the sums of binomial probabilities converge to normal probabilities. Now, there are two applications that I would like to do. One is, first of all, a practical application. This particular theorem has a lot of very practical applications. And so I'm going to show just one of them. And then it has theoretical applications. The theoretical applications has to do with random sampling. It has to do with simulations. It's very crucial to understand this in simulations because the accuracy of simulations depends on this. So there are two areas that I want to cover. First area is just a simple application. This is a practical illustration. Then I will move to the theoretical in accordance with the principle that first you should do things in concrete, then you should do things in general. So this is actually what happens in voting. Suppose that we have a population, we have a district which has a population of 10,000 people. I want to find out how they are going to vote. And suppose there are only two candidates, one is Nawaz Sharif and the other is Imran Khan. And now, how can I do that? Well, one thing I can do is to go and ask everybody, but that's very expensive. So what I do is I pick a random sample of 300. As we have said, this is not going to be done by just standing in the central square of the district and picking up people who are passing. Although many people do that, and then they get wrong results because such a sample, if you just ask people, okay, who are you waiting for? So you ask 100 people. You stand in the city square and people are passing and you ask 100 people and say, okay, I took a sample. This is what is called a convenience sample because it's very convenient. You don't have to do any work. Now the thing is that convenience samples are no good. You can, on one day if you stand, you will get one result. On the other day you stand, you get another result. And you cannot say anything using the convenience sample. But if you do a real random sample is hard because you have to first list all of these 10,000 people and then you have to use some procedure which selects in such a way that every single person has exactly the same chance of being selected, which is 1 over 10,000. So it's very hard to do, very hard to pull a correct random sample. In fact, most people don't do that. What we do is we do a clustered sample. It's very hard to do because you don't know how many people there are and it's very hard to find out. But you can count the number of houses. If you count the number, okay, so there are 100 houses. Now each house has a different number of people in it. So a number of houses is not the same as the number of people. But you can say, okay, I will take a random sample from the houses and then from within the house, I will choose at random the number of people. And so if one house has 7 people, so I choose a random sample from the 7 people who are eligible for voting. So I choose one of them with probability 1 over 7th. So this is a multi-stage, it's a 2-stage cluster sample because at the first stage we randomized among the households And then at the second stage, we randomized among the members within that household. And this is what is continuously done. In this case, of course, all people do not have equal probability of being selected. Because in a house where there are small number of people, the probabilities of your being selected is higher. In the house with large number of people, your probability of selection is lower. But you can calculate the probability, and this is what matters ultimately. So the random sample may not be equal probability, but as long as you can calculate the probability of every selection, you're okay. Anyway, so we take a random sample of 300 voters. In this sample, we go and ask everybody, who are you voting for? And so we find that 175 people are voting for Nawaz Sharif in our sample, and 125 people are voting for Imran Khan. So now, one thing to understand, very important, is that some probabilities we can calculate, some we cannot. So we have to know what are the things we can calculate, what are the things we cannot calculate, and then the thing that we would like to know, we cannot calculate. So what we'd like to know, what is the probability of Nawaz Sharif winning on the basis of this sample? But this question even doesn't make sense, because what in this district, suppose that the election will be done in this district and vote will go 1-4, so we don't take into account others. Because under the situation we are imagining, either Nawaz Sharif has won or he has lost. There is no question of probability. Because in this sample, we are assuming that everybody has already made up their mind. We are not considering that people are going to decide. If everybody is undecided, then our random sample is just going to be random noise. It's not going to tell us anything. So we are assuming that everybody has already decided who he is voting for. Maybe there are 7,000 people who have decided to vote for Nawaz Sharif, and 3,000 have decided to vote for Imran Khan. So in this situation, then Nawaz Sharif is going to win. If 6,000 have decided for Nawaz Sharif, he's still going to win. If 4,000 have decided for and 6,000, then he's going to lose. But whatever the case, this is something that's already fixed. It is not something which has a probability. So we cannot even think about the probability of Nawaz Sharif winning. We can talk about, okay, I'm going to learn something and I'm going to make a statement. I'm going to make a prediction. This is exactly what Gallup does. Gallup takes a sample and then he says, okay, I predict that Nawaz Sharif will win. Now there is something we can calculate. What is the confidence that we can have in such a statement? It is not how many times will be true, how many times will it be false. So maybe if it's a 95% confidence, then in 20 elections, Gallup will be wrong once. So basically, if you know what the population is, then you can calculate the probabilities of the sample. If you know what the sample is, you cannot calculate probabilities for population. So only one direction the probability calculation is possible. So the way that this proceeds is by saying that, okay, let us assume that there are 5,000 voters, which is exactly the critical balanced point. 5,001 will make the election go for Nawaz Sharif, and 4,999 will make it go for Imran Khan. So we can say, okay, we put the null hypothesis. This is where the hypothesis comes, because the thing that we want to calculate, we cannot calculate. So what we do is we go backwards and we say, okay, let's calculate some of those things which we know how to calculate, and maybe from this knowledge we can learn something about the thing that we are trying to find out. And this is exactly how it works. So we do the probability calculations that are possible. So we assume that there are 5,000 voters for NS, Nawaz Sharif, and then we ask what is the probability that in a sample of size 300, Nawaz Sharif will get 175 votes. Okay, so now we switch to this, and chocolate for the one who tells me the Excel formula for how to calculate what I want to do, which is to find out the probability that the sample size, that given a random sample of 300 from this population of 10,000, if the vote is exactly balanced, there are 5,000 voters for Nawaz Sharif, 5,000 voters for Benazir, Imran Khan, and so 175 is what was observed. I want to ask, what is the probability of seeing 175 votes for Nawaz Sharif in this situation, in a random sample of size 300? So what should I put here? First of all, I have to start with the letter B. Binom. Okay. Binom dot dist. Parentheses. What? 175 is my K, comma, N is 300, 0.5, okay, Taru. That was Maria, I think, huh? Kuptia, who was the biggest voice. There were many other voices. Okay, so it's what? Oh, I made it cumulative. I didn't want the cumulative. Okay. So this is the probability of seeing up to 175, which is 99%. That's not the number that I want. Okay, let's calculate the probability for the 125, right? Yeah. Yeah, 125. Okay, that will be the opposite of this. So what's the probability that Imran Khan will get some number? You see, there is an issue of direction here which requires some experience and learning. The sample is obviously against Imran Khan and in favor of Nawaz Sharif. It's 175 is bigger than 150, 125 is less. So we want to ask that what is the probability of seeing something this unfavorable or more unfavorable? Now, explaining this requires some why this, and it requires some work, and I have done that in some lecture, but it will take some time. And this right now I'm not concentrated on that issue. Right now we are working on the asymptotic properties of binomial and how to do binomial calculations. This is my goal. So I'm not going to work on explaining the confidence intervals. But basically the probability that we are interested in is the probability of seeing an exceptional outcome and adding to it all more exceptional outcomes. So 125 is pretty bad, and all the worse outcomes are also going to be included in order to get the confidence probability. So that is now 002. So this is the probability of observing 0 or 1 or 2 all the way up to 125 votes. So Imran Khan, so we are going to reject the hypothesis that Imran Khan will win. The confidence with which we can reject this is 0 is at the opposite of this, 998. It means that in 1000 elections, 2 of the times, maybe 3, 2, yes, 2 to 9. 2 of the times we will be wrong, and 998 times we will be right about this. Now this is not so easy to explain or prove, but we just take it for granted right now. So the confidence with which I can predict a Nawaz Sharif victory in this with this is 998, 99.8% confidence. Okay, so that's one example. Now, the other thing I want to do is all right, so alright, so this is another way to formulate this same material that we are looking at. You see, what we do is we have an event. The event is, okay, let's see. The event is that we give this drug for polio to the patient, and the patient is cured. Now, I don't know what is the probability of cure. You can think of dengue also. That okay. In the last time we were discussing, we said that the probability of cure is 70%. But now suppose we take the same hospital and we have a cure for dengue, but we don't know how effective it is. So now people start coming in at random. Now we think that, and this is not a correct assumption, but let us pretend that people come in at random to the hospital. So every person has an equal chance of catching dengue, and when they catch it, then they come to the hospital. Again, this is completely wrong, but suppose that it is true just for the sake of making the calculations. So then people start coming in, and each person who comes in with dengue, I give him the drug, and then I record 1 if he survives, and I record 0 if he doesn't. And so now I have 100 patients have come in, and 65 of them recovered. So now I want to know what is the probability that my drug will cure the dengue. Now, as I said, this is the reverse calculation. It cannot be done because I have the observations, but the true probability I don't know, and it cannot be computed. So, but there are some things which can be computed, and these things which can be computed allow us to make a confidence statement. So what is the things that can be computed? So we just put P as our unknown true probability, and then we do calculations about T, which is the observed frequency of the event. So T is the 65 patients recovered. So N is 100. So the observed frequency of the event E is recovery from disease, is observed frequency is 65%. T over N. 65 case recovery, N is 100. So then our central limit theorem says that T over N is approximately normal with mean P and standard error equal to square root of P times 1 minus P over square root of N. This is just a restatement of the same theorem that we just discussed. So we can say that T over N is normal with mean P and standard error square root of P 1 minus P over square root of N. Equivalently, if we define Z equal to T over N minus P over the standard error, then Z is standard normal. These two statements are equivalent. So one of the things that you can say is that, okay, T over N is normal with mean P, So T over n minus P is normal with the mean 0. This is one part of standardization. Okay, if you subtract the mean from a normal variable, the mean becomes 0. And then its standard deviation is same as before. Adding or subtracting a constant to a normal doesn't change the standard deviation. So the standard deviation will be 2.6. Standard deviation will be square root of p times 1 minus p over the square root of n. Right? Now, one very important thing that we want to say here is that, equals norm dot s dot dist of, let's just put 2.6 comma true. This is, what happened? 99.5%. Okay. Now, there are some numbers that every statistician must know by heart. One of them is 1. If you have a standard normal distribution, then the probability of x being between minus 1 and plus 1, how much is it? 68%, yes. So, actually, 68%, you should think of it as 2/3. 66.6%. It's 68, but 2/3 probability. 1/3 is left out and 2/3. And then what's the probability of being between plus or minus 2? 95%. This is where our standard confidence interval comes. And then what's the probability of, what is the 99% confidence interval for standard normal? What? No, not 3. It's 2.6.
2.6.
Yeah. 99.5 is the probability. There's only 0.5% probability above 2.6. And there is another 0.5% below minus 2.6. So between minus 2.6 and plus 2.6, I have 99% probability. So a 99% confidence interval is 2.6 times the standard error. Which means that if you have a normal variable with standard error s, then the probability of x between minus 2.6 times the standard error and plus 2.6 times the standard error is 99%. So that's what we are saying. Yeah, this statement, this is very important, crucial. Probability that the observed frequency minus the true probability is between these two numbers is 99%. Now, this is a probability statement if t is random. If I'm taking a random sample, then I can say that the observed frequency. So if p is 70%, then I can say that, and I can calculate the standard deviation. Okay. So I'm taking a sample. Let me explain. There are two statements. One statement is, and this is the last point that I want to make. So I have the true probability is 70%. I take a random sample of size 100, and I calculate the standard deviation, which is 4.58. So I can say that, suppose I want to make a 99% confidence rate. I want to say something about how many voters for Nawaz Sharif will I observe, or actually that's not the right one. How many cures for dengue I will observe. Now this time this is a hypothetical situation because this will never happen. I am assuming that I know the true probability of cure. This is not going to work most of the time. Sometimes it works, but very rarely. There are some. So now, assuming that I know the true probability, I want to make a 99% probability statement. What is the probability? So I know what to do. I need to do 2.6 times 4.5. I have my calculator here, so I can do that. 2.6 times what? Oh, 61. Yeah. Times 4.58 was it? 4.58 I think equals 11.9. Okay, so I know what I need to do. So I have 70 plus 12 is 82 and 70 minus 12 is 58. Yeah. So I can say that the chance, if I say that, okay, you will see about between number of cures will be between 58 and 82 with 99% probability, I will be right. And this is also what we saw from the table, that probability started becoming visible at 58. So I can say that with probability 99%, the number of people who get cured will be between 58 and 82. This is a probability statement, but this probability statement I will never be able to make because I will never know the true probability. But what I can say is that the difference between the true probability and the observed frequency will be less than 12 with 99% probability. Okay. Now there are two meanings of this statement. In one meaning, if the observed frequency is a random variable, then this is a probability statement. But if the observed frequency is observed, now I take a sample and it has 65 as the observation, then I can say that, okay, 65% minus p will be around, the difference will be around 12 with 99% probability. So I can say, okay, take 65% and take plus or minus 12. The true probability is probably in there. Now there are two complications with this. This is actually not true. Even there is a double approximation that is going on. One is that I have used a standard error, but I don't know the standard error because I calculated on the basis of 70, but I don't know whether the probability. I don't know anything about p. I only have the observed frequency. So I say, okay, let's approximate p by 65% because that's the observation. So this may or may not be true, but actually it works practically. That's why we're using it. So one approximation is, okay, set p equal to 65%. It turns out that it doesn't change the standard error very much to go from 65 to 70. So 4.5 is still correct, 4.6. Then n is of course known. So I can say that, okay, 65% plus or minus 12 contains the true probability. This is my confidence interval. But if I say, okay, here is my statement, 65% plus or minus 12%, the true probability is 65 minus 12 kitna hota hai? 53% and 87%. So if I say that the true probability is between 53%, true probability that this drug cures dengue is between 53% and 87%, I can be 99% sure that this statement is true. But this is not a probability statement because the statement itself is either true or false. The true probability is fixed. It is not a random variable. So this statement is either true or false, but the probability of its being true is 99%. Okay. So that's the theoretical part. All right. That's all for this lecture.